Hello everyone, welcome back to Diksha Karnataka YouTube channel, and you are watching your favorite KCET 2026 series Sankalp, right? Today I am going to discuss a new chapter, moving charges and magnetism. I have already completed a few chapters. You can check that in the playlist of our channel, and obviously for that you have to subscribe to our channel and join our WhatsApp channel. The link of the WhatsApp channel is given in the description of this video. Without any delay, let us start with the part 1 of moving charges and magnetism. Here we are going to learn about Lorentz force and moving charges. So let's look into the chapter distribution. So here is the complete topic distribution of the chapter: Lorentz force, motion of a charge in magnetic field, magnetic force on a current carrying conductor, magnetic field due to a current element, applications. In that part of application we have magnetic field due to straight conductor, circular current carrying loop, and in the magnetic field due to a current element, Biot-Savart's law is also there. Now in the other part we have magnetic field versus electric field comparison and the relationship between mu naught and epsilon naught, very important. In the third part we have Ampere's law, Ampere's circuital law basically. In the application part we have straight conductor, solenoid, and force between two parallel current carrying conductors. Last is torque on a rectangular current loop, circular current loop as a magnetic dipole, galvanometer, ammeter, voltmeter. So galvanometer to ammeter, galvanometer to voltmeter, everything is included in this chapter. Now today we are going to study up to this part. Okay, so everything on my right hand side we will study in this lecture, and tomorrow we will study whatever is on my left hand side, right? So let's start with the first part, introduction. So introduction, you have already have a basic idea that whenever a current carrying conductor or a moving charge, it always produces a magnetic field, right? So let's see, moving charges or current produced magnetic field in the surrounding space. So whenever there is a current carrying conductor or some moving charges, it will produce a magnetic field, right? If you remember in the past when you were studying in class 10th, you have studied Oersted law, Ampere's swimming law, or right hand law. There are few laws that you have studied, so go back to your class 10th and revise them once if you have forgotten everything, right? I will help you to try to remind you as much as possible. So here is one of the part where we have a current carrying conductor carrying current out of the page. Okay, so magnetic field lines are aligned like this. So if you and in this case it is cross, that means current is being carried into the paper and the magnetic field is in the opposite direction. So you have to use your right hand rule to find the direction of magnetic field, especially for current carrying conductor. So if the current is out of the page, your point your thumb towards the direction of current, and if you curl your fingers, that will give you the direction of magnetic field. For current carrying conductor, it is basically a circular loop, closed loop. Okay, and for us moving charge, similarly you can find the direction of magnetic field based on the direction, as well as if the charge is positive or negative, based on that you can find the direction of magnetic field, but it will be a circular magnetic field, right? Now let's move on to the next important concept which we will study for the first time, which is Lorentz force. Okay, so Lorentz force, obviously the name of the person, Lorentz is the name of the person. Okay, he actually combined two different forces. One force we have already studied. What is that force? That is force due to electric field. Suppose we have a charged particle, and we kept it inside an electric field. We have a charged particle Q and we have a electric field, say E. Okay, vector. Obviously electric field is a vector. Now what will be the force acting on this charged particle? The force acting on this charged particle, if the charge is positive, assuming the charge is positive, it will experience a force in the direction of electric field, and the magnitude of that force is given by Q into E. In fact, it will be Q into E vector. Q into E vector, that will give the direction as well as magnitude of the force. Now in case the charge is negative, the direction becomes opposite because Q is negative. So Q negative means minus QE means the force will be in the opposite direction. Okay, that's it. So force acting on a charge is given by Q into electric field vector. Now force due to a magnetic field. Now force due to a magnetic field is very, very interesting. So when a charge particle, if you have a similar magnetic field, suppose symbol for magnetic field is given by B, okay, electric field is given by E, and magnetic field is not given by capital M, it is given by B, okay, because M has lot of other different meanings, that's why magnetic field is represented by the symbol B. Okay, now if you have a charge particle and it is moving with the velocity v, charge particle, we will see that in later part that static charge particle do not experience magnetic force. Okay, so charge particle which is moving with the velocity v in some direction, then the force due to magnetic field is given by Q into V cross B, Q into V cross B. Okay, this is called magnetic force. Now if electric and magnetic field both exist in a region, suppose we have an electric field, we have some magnetic field as well, then what will be the total force on the charge? We have an electric field as well as a magnetic field, then what will be the total force acting on the charge? The total force acting on the charge is given by F equals to Q common from both cases, Q is common, E plus V cross B, E plus V cross B. This is called Lorentz force. This force is called Lorentz force. Force on a negative charge is opposite to that on a positive charge. So as I said, if the force acting on a positive charge, say in the right hand side, then force on a negative charge will be on the left hand side. Very important concept to remember, because sometimes they will ask you simple Lorentz force related question, but they will ask based on an electron. Electron is a negatively charged particle, so whatever is the conventional direction, conventional means positive charge. So if you consider a conventional charge, the direction will be due to a positive charge. But if they change the question and they ask you that what will be the direction of force on an electron, then it will be whatever direction you have calculated, it will be exactly in the opposite direction. It will be exactly in the opposite direction. So be careful, clear your mind on this doubt. Many students confuse between charge particle positive and negative, and it is very common for the question paper setter. They will try to confuse you to check whether you have a basic concept or not. This is a very basic concept, that whatever force acting on a positive charge will be exactly opposite for a negative charge. The vector product makes the force due to magnetic field vanish or become zero. Vanish means become zero, magnitude becomes zero if the velocity and magnetic field are parallel or anti-parallel. For example, the diagram I have drawn, in this case you can see that velocity is parallel to the magnetic field. So if velocity is parallel to the magnetic field, then the component of magnetic force becomes zero. Okay, generally this force is represented by Fe, okay, vector, and this is represented by Fb. Okay, Fb means magnetic force, Fe means electric force. Okay, that is the general convention. Okay, so Fb becomes zero if the velocity is parallel or anti-parallel. If the particle is moving parallel to the magnetic field or anti-parallel to the magnetic field, okay, the magnetic force will be zero. Magnetic force will be zero because it is V cross B. V cross B means what? If you take in terms of scalar quantity, then V cross B, what is the magnitude of V cross B? The magnitude of V cross B is Vb sin theta, right? So magnitude is Vb sin theta. So in case of parallel, theta is 0. In case of anti-parallel, theta is 180 degree. So in both cases, sin theta is 0. That's why the magnetic force becomes 0. And the magnetic force is 0 if charge is not moving, then velocity v is 0, and only moving charges feels the magnetic force. So that's what I was saying, that if v is 0, then this entire quantity will be 0. Does not matter, 0 multiplied by 1000 is 0, right? So if you multiply with 0, then entire thing becomes 0. So only moving charges experiences magnetic force, static charges do not experience magnetic force, right? Now let's move on. Let's see one question. A proton moves with a velocity of 5 into 10 to the power of 6 j cap meter per second through an uniform electric field of E equals to 4 into 10 to the power of 6 2 I cap plus 0.2 j cap plus 0.1 k cap volt per meter, and an uniform magnetic field B equals to 0.2 I cap plus 0.2 j cap plus k cap. This 0.2 is common. The approximate net force acting on the proton is. Okay, so first of all we have to understand this is a proton. This is a proton, and for the starters we will assume the charge of a proton is equals to E. We will put the value of E. Obviously E value we already know, 1.6 into 10 to the power of 19, but for ease of calculations we will use it as E, and the last point we will put the value. Okay, first let us find the electric force. What is electric force? Electric force is given by Q into E, E vector, right? Q into E vector. Now what is the magnetic force? Magnetic force is given by Q into, and for starters, as I said, the charge I will mention as E, so let me write it in terms of E. The second part we will start with E itself. So Q into V cross B. Q is E, right? V is this value cross B. Okay, now how to do the cross product? Okay, so if you remember that I J K, so I cross J gives you K cap, and K cross I gives you J cap, J cross K gives you I cap. If you go in opposite order, then it will be negative. For example, I cross K is minus J cap, K cross J is minus I cap, and J cross I is minus K cap, right? So, and also there is another method, determinant method, I cap, J cap, K cap, right? This is determinant method. You have already studied determinants in mathematics. So what is V? V is only J cap, right? Only J cap means this is 0, 5 into 10 to the power of 6 J cap. This is also 0. What is magnetic field? Magnetic field, 0.2 is common, so we can take that 0.2 over here as well. So we will only put these values over here. So 1, 0.2 and 1. Now let's do the multiplication, right? So first is I cap. Exactly the way you do the determinant, first you take this column, cover both of them and multiply these two. So 5 into 10 to the power of 6, right? 5 into 10 to the power of 6. Then you have 0.2 into 0, so plus 0. Now if you are using plus J or minus J for middle column, if you are using minus symbol, that is also fine. If you are using plus symbol, that is also fine. I generally use plus symbol, so let's do it. So we crisscrossed it, so 0 was our last position, so 0 into 1 is 0 and 1 into 0 is another 0, right? Plus actually the center it will be minus anyway, does not matter as it is 0. And last is K cap. K cap is 0.2 into 0 is 0 and 1 into 5.6, 5 into 10 to the power of 6, right? There will be, sorry, it will be 0 minus 5 into 10 to the power of 6. right? Now what will be the value of FB? Now FB will be E into 0.2. This 0.2 we have taken outside, right? And V cross B we have calculated. It will be 5 into 10 to the power of 6 I cap minus 5 into 10 to the power of 6 K cap, right? Now 5 into 10 to the power of 6 will also be common, so E into 5 into 0.2. 5 into 0.2 is 1, right? 2 5s are 10, point is there, so it will be 1. So it will be just 10 to the power of 6 I cap minus K cap. J cap is 0, no J cap involved in this. Now let us add these two vectors. E vector is this one, right? Now let us add these two and let's see what we are getting. So F Lorentz force equals to Fe plus Fb. Remember, we have to find the magnitude, so we will do that in the last stage. So E is common, and 10 to the power of 6, 10 to the power of 6 is common, right? Now what we are left with, we have 4 into 2, that is 8 I cap. 8 I cap. 4 into 0.2, that is 0.8 J cap, plus 4 into 0.1, that is 0.4 K cap. Okay, and what we have here? Here we have I cap plus, minus K cap, right? Now we have to simplify this. So E into 10 to the power of 6 and 1 plus 8 is 9 I cap plus 0.8 J cap minus 0.6 K cap, right? 0.4 minus 1 minus 6. Now they asked you to find the approximate value, not the exact value. Okay, so you can, what you can do, you can square them up and add them up. How to you know how to find the magnitude for a vector. If you forgot, just let me remind you once. So if you have a vector, say Ax I cap plus Ay J cap plus Az K cap, then the magnitude, this is a vector A, then magnitude of A is given by square root of Ax square plus Ay square plus Az square, right? This is how you find the magnitude of a vector. Now in this case, it is very interesting to see that the coefficient of J cap and K cap are very, very small, 0.6. Okay, so what we will do to calculate the magnitude of this vector, we can safely, because the question is also about approximate value, we can safely ignore this and this for now. Okay, we will not consider this, we will only consider the 9. Okay, so this one is 0 almost, this one is almost 0, so only Ax square, that means only Ax is the magnitude for this particular case. Okay, so what we will do, we will just put that value in our calculation and we will try to find what is the value of the Lorentz force. So the magnitude of Lorentz force is given by E. E is 1.6 into 10 to the power of minus 19. Now we will put that value into 10 to the power of 6 into 9. Only this 9 we are taking, rest of the terms we are ignoring, and because its magnitude I cap is not coming over here. Okay, so now let's do the multiplication. You will get 9 ones are 9, 0.6 36, 3.6, so it will be 12.6 into 10 to the power of minus 13. Okay, so 12.6 into 10 to the power of minus 13, which is very, very close to which one? This one, 12.6. Right, we have ignored 0.8 and 0.6, so if you have added them, then the answer would be close to this value. So correct answer is 15 into 10 to the power of minus 13. This is the approximate value. Okay, so approximate value, because you are trying to find approximate value, it is very important you do the approximation yourself and try to find the closest possible value. Okay, and because you have omitted two points, omitted two values means actual result should be higher, slightly higher than whatever you have calculated. It should not be too much high, it should not be too much low, it should be slightly higher than your calculated value. 15 actually matches that description, so correct answer will be 15. Now, do not use calculators to solve these questions. It's very important to stop using calculators, because in the final exam you are not allowed to use calculators. So train your mind for do not use calculators. Stop using calculators right now. Now, motion of a charge in a magnetic field. So now what we have, a charge is moving in an uniform magnetic field, we will experience a force. Right, we already know that if charge is moving in an magnetic field, it will experience a force. Now, in case they are parallel or anti-parallel, the force will be 0. Otherwise, if they are not parallel or anti-parallel, in general case, theta is not 0 or 180 degree, so it will experience force. This force acts as a centripetal force. It's very interesting. Then in case of moving charge in a magnetic field, already existing magnetic field, the force that acts on the charge is basically mutually perpendicular to V and B. So mutual perpendicular vectors means it will basically try to rotate in a circular motion, and that circular motion means this is basically the centripetal force. You have to remember that, and produces a circular motion perpendicular to the magnetic field. So the force acting on this charge will produce a circular motion just like this. As you can see here, we have a charge particle and it is moving, suppose in this direction. The magnetic field is into the page of the paper, then the force acting on this V cross B will be towards the center of the circle, and it will start rotating in a circular motion. Okay. If the velocity has a component along B, now suppose the velocity B and V, they are not exactly perpendicular. V and B, they are not exactly perpendicular, they have certain angle, so that they have a component which is not parallel to the which is not perpendicular to V, but it has a component parallel to B. Then what happens is that along the magnetic field will not be affected by the magnetic field. So the component, suppose the V is no longer parallel, it has some direction. So if you consider some angle, then there will be a parallel and one will be perpendicular component. The parallel component will not experience any force. The parallel component will not experience any force due to the magnetic field. So that motion will continue as it is, right? So what will happen? It will give rise to a helical motion. So it will give rise to a helical motion. So as you can see, the V has a component, it is not perpendicular to the velocity. Okay, it has some component. Okay, so what happens? Perpendicular component is there and parallel component is there. Now parallel component will take it in the forward direction, whereas the perpendicular component will try to make it rotate in the circular path. So both motion will happen together, and this motion is called helical motion. Helix, the spring. Okay, the shape of a spring basically. If you have seen the spring inside a pen, or if you have played with spring, so that spring design is basically, the spring is called a helical shape, and this kind of motion you will observe. Now remember that there are some angles. If the angle theta is 90 degrees, then it will be a perfect circular motion. If the angle is between 0 and 90, it will be a helical motion. Okay. Now we have to find the radius of this path, which is very important. The radius, the angular frequency, the time period, these are the very important things. So as you know that the force acting on this charge particle, as I said, this is a centripetal force. The force acting on this particle is actually a centripetal force. Okay. Now from the centripetal force we can say that what is the formula for centripetal force? Centripetal force is given by mv square by r. It is always the same formula, okay, and it has to be provided by something. In this case, who is providing the centripetal force? The magnetic force is providing the required centripetal force. So what is the centripetal force? Centripetal force is QVB. Centripetal force is QVB. Sin theta, QVB sin theta, but sin theta is 1 because perpendicular motion. In this case, V and B are perpendicular. Theta is 90 degrees, right? Theta is 90 degrees. Okay, so that means sin theta is 1, right? So from there we can write mv square by r is directly equals to QVB. Okay, and if we just calculate the value of r from this equation, we can see that r is equal to mv by qb again. So this is one expression. This is the radius of the path. Okay, now if you just simplify v will be qbr by m. Why we are simplifying v for that matter? Because we want to find the angular frequency, and for angular frequency we know that v is equal to r omega. Okay, v is equal to r omega. So for that reason we are also trying to find v. This is not super important, but okay, this much is required to maintain the circular motion. Now angular frequency v is equal to r omega. So just put that r omega in this equation, or you just simplify omega is equal to v by r, divide this by r, and you will get omega is equal to qb by m. This is also very, very important expression. The time period is given by 2 pi by omega. Just put this value, so it will be 2 pi m by qb. Okay, so 2 pi m by qb is the time period. Right, so these expressions are very, very important, and based on these basic formulas in your PU board the derivation might come, and in your KCET exam maybe objective questions, MCQ questions will come from this based on this formula. So you have to remember these formulas as well. In case you forget, then you have to start from this relation every time. Right, if you practice this 2-3 times, then you will always be able to remember. You have to understand that this is the centripetal force and this is the Lorentz force of the component. Right, this is the Lorentz force of the component. So if you are comparing these two, you can calculate r, you can calculate v, you can calculate omega as well, and time period as well. Let's see one question. A proton, deuterium and an alpha particle having the same kinetic energy are moving in circular trajectories in a constant magnetic field. Okay, if Rp, Rd and R alpha denote respectively the radius of trajectories of these particles, then which of the following is correct? So you have to understand this. In nuclear physics the introduction to deuterium and alpha particle will happen, but for now you have to remember that proton has, if proton has a mass 1, for example, if proton has a mass 1, then a deuterium will have a mass 2 and an alpha particle will have a mass 4. Okay, so if I say that mass of a proton is simply m, mass of a proton is simply m, then that of the deuterium will be 2m and alpha particle will be 4m. Now you will say, sir, it is very simple, then velocity is given and we can simply find the radius of curvature. So you can say that, okay sir, this is the formula, so we can say that mass of alpha particle is more, so radius of alpha particle will be more. It is not that simple. Why? Because velocity is not given in this question. What given is that kinetic energy is same. So kinetic energy same means what? Kinetic energy same means half m v square are same for all the particles. Okay, so what we have to do, first we have to convert this equation in terms of half m v square and then we can compare, okay, which one will be greater. So for that what we will do simple thing, we will square both sides, and m square v square by q square b square. Okay, so this is the starting point and from here what we will do, we will do m by q into q square into b square into mv square, and we will multiply with half and 1 2 over here. So now as you can see, this is kinetic energy. So from here we can write r square equals to 2m by q square b square into kinetic energy k. Here this is k, right? This is called kinetic energy k. Now what we will do, we will take a square root of the entire thing and we will see that it is basically 2m square root of 2m into k divided by qb. So now if kinetic energy is constant, we can say that radius is inversely proportional to the mass. Radius is sorry, not inversely, proportional to square root of mass. Okay, so definitely higher mass means higher radius. Higher the mass, higher is the radius. So alpha particle will definitely have greater radius than that of deuterium and that of the proton. So correct relationship is R alpha is greater than RD greater than RP. Clear? So they have tried to make the question slightly difficult, and this is from a question came in Comet K exam. Now let us continue with our discussion to the next concept, which is magnetic force on a current carrying conductor. So here we have, so far what we are discussing? We are discussing force on a moving charge. Now what is current? Current is multiple moving charges, right? So what is that? So if you consider a conductor which is carrying a current in particular direction, a conductor carrying a current in the particular direction, then it will also be affected by the magnetic force. Now what will be the direction of the magnetic force? The direction will be, to find the direction as well as magnitude, we will use F is equal to I into L cross B. What is L vector? L vector is a length vector. Length vector means obviously the length of the conductor, and it is in the direction of the current. L vector is in the direction of the current. So L cross B means, again you have to use right hand rule, L cross B means obviously is this. So you will get the direction of the force, right? So L cross B, it will be into the page of the paper. L, start from your first vector L, and then you curl it towards the second vector, then your thumb will give the direction of the vector. That is the cross product rule. If you remember, that is very good. If you don't remember, just I am explaining it to you. So A cross B means first you point your fingers in the direction of A vector, A cross B, right? So A vector first, B vectors next, and whatever will be the direction of the thumb, that will give you the direction of the resultant vector. Okay, so this is the resultant vector, cross product of L cross B. In terms of magnitude, it is BIL sin theta, BIL sin theta. Okay, BIL sin theta. This is very, very important. You have to remember this formula for multiple uses. Okay, based on Comet K, KCET, JEE, board exam, BIL sin theta is one of the most important formula. Now Biot-Savart's law, the most important law of this chapter. Ampere circuit law is also important, but we will study that in our next lecture. So Biot-Savart law is the most important formula for today's lecture. Suppose we have a current carrying conductor. We have a current carrying conductor carrying current in this direction, and we have a small current element dl, a very small current element dl. This is dl. Okay, and due to this small element, we want to find the magnetic field at point P. Why small element? Why not because of the entire wire? Because the entire wire may not be very, very regular. If it is a regular wire, that like a straight wire or a circular wire, you can use Biot-Savart's law to calculate the magnetic field. But if the wire is not straight, if it is a curved line, then also Biot-Savart law is valid. Okay, Biot-Savart law valid for any type of current carrying wire, but sometimes what you have to do, you have to use element concept, okay, small element, and then you have to take the integration based on the geometry of the wire. Okay, so here the Biot-Savart law basically gives you the magnetic field due to a small current carrying element dl at certain point P. Now what to do? First you have to see what is the length of the element dl, what is the direction of the current, and the distance of the point r, also the angle that it makes with the direction of the current element. How to find the direction? So if you have a curve, how to find the direction at this point? You have to take the tangent. The tangent will give you the direction of the curve, right? So you have to draw a tangent at this point, and tangent can be drawn in both sides. Now which direction we will choose? We will choose the direction which is in the direction of the current at that element. So current is flowing in this direction, so current is flowing like this, right? So we will consider this as the direction of the element. Okay, as simple as that. Now what is Biot-Savart's law? Understand this, you don't need to remember or memorize anything. If you understand this concept, you don't need to remember or memorize anything. First is the magnetic field at point P is proportional to the current I. Now why we are writing as dBp? dBp means the magnetic field due to the small element, magnetic field due to the small element. That's why it is also differential. Okay, because the element is differential, the magnetic field is also differential. So it is proportional to the current I, it is proportional to the length of the element. Okay, current obviously it is proportional to current, more magnetic field, and dl element, if you are considering more length, that means more magnetic field. It is inversely proportional to the square of the distance, same as Coulomb's law, right? So it is inversely proportional to the square of the distance, so 1 upon r square, and it is directly proportional to the sine of this angle theta. It is directly proportional to the sine of this angle theta. Now if you combine all these formulas, there has to be one constant, mu naught by 4 pi, right? It is similar to that of the Coulomb's law. If you remember, in case of Coulomb's law, what was the constant? Constant was 1 by 4 pi epsilon naught. Here, instead of epsilon naught over here, there is a mu naught in the top, right? So almost similar to that of Coulomb's law, but it is in case of magnetic field and IDL sine theta. So here IDL is important, and if you write the values of mu naught by 4 pi, then it will give you mu naught by 4 pi is given by 10 to the power of minus 7 Tesla meter per ampere. Okay, you can even write this as in terms of vector as well. So let me know if you know the vector form. Okay, I can discuss that in future lecture, but for now you can also write this in a vector form. We are not going into the vector form, and that will be little bit deep, complicated, but you can write this as a vector form as well, because magnetic field is a vector quantity. And this is for you, for your homework. Okay, write down the vector form in your notebook and keep it safe. Okay, mu naught is called permeability of free space. So epsilon naught was permittivity of free space, and mu naught is called permeability of free space. Now let's see one question. The magnetic field at origin due to a current element dl. Okay, I think I need to give you the vector form to solve the next question, otherwise next question will not be able to solve it. Okay, so let me give you the vector form as well. So what is the vector form? In terms of vector form, the same thing can be written as vector is mu naught by 4 pi, okay, I, dl is a vector, length vector, cross r cap vector divided by r square. Okay, so what is the direction of dl vector? Dl vector is in the direction of this. Okay, so this is dl vector, and r cap is obviously in the direction of the position vector, so this is r cap. Okay, unit vector. So dl cross r cap divided by r square. Sometimes same thing can be written as mu naught by 4 pi I dl vector cross r vector, not unit vector, divided by r cube. But that does not mean that it is proportional to 1 upon r cube. Very important. Why? Because it is actually in terms of unit vector. If you want to convert a unit vector to a full vector, then you have to multiply with the magnitude, right? You are multiplying r in the top and bottom, and that's why this r cap vector is now complete r vector, right? That is why there is one extra 3 is coming, one extra r is coming in the denominator, but that r will be absorbed by this r cap, and sin theta is only there when you are not writing in terms of vector form. In vector form, sin theta does not come. Now let's see the next question. The magnetic field due to the at the origin due to a current element dl vector placed at a point with the vector position r cap is. So same r cap known, r vector is. So the question is same as the formula that we have written. So if you see that it is Biot-Savart's law, only thing you have to be careful is that because you are writing r vector, the denominator will be r cap and not r square. Okay, so be careful with such questions because you are writing, if the same thing was written as r cap, then it will be r square, but because it is written as r vector, it will be r cube. Okay, if you have any more doubt, please mention that in the comment below. Now magnetic field due to a straight conductor, magnetic field due to the straight conductor can be derived using Biot-Savart's law, but we will do this derivation once we learn Ampere's circuital law in the next class. But for now, the formula that you have to remember is that suppose you have a very long infinitely current carrying wire, or you have a finite current carrying wire. So for finite current carrying wires, so the wire is long but it is not infinite. So if you join this point and the point of inspection, point P, where we are trying to find the magnetic field. So if you join that, this angle is theta 1 and this angle is theta 2 from the bottom. This is the perpendicular distance from the current carrying wire, right? So this is the vector, this is the quantity r. Then magnetic field at P is generally given by mu naught I by 4 pi r sin theta 1 plus sin theta 2. This is the expression for magnetic field due to a current carrying wire which is long. Okay, this is the formula. Now if the wire is very long, the theta goes to 1. Okay, the theta goes to 90 degrees. So infinitely long wire means the angle becomes 90 degrees. This angle will also become 90 degrees. So sin theta plus sin theta 2 both will be 1 plus 1. Sin 90 is 1. So 1 plus 1, so both will be 1, so it will be 2, and you have, if you multiply with 2, you will get mu naught by 2 pi r into I. Okay, so mu naught I by 2 pi r, that is the general formula, right? So this formula is important if you are preparing for JEE or Comet K exam. I have not seen a KCET question coming out directly from this formula, but JEE and Comet K students, you have to learn this formula. For students who are studying only for KCET, this formula is sufficient. Now current carrying circular current loop. This derivation I have done in one of my theory video for this same chapter, and I will do it again in future theory videos, but right now I am not super interested in this derivation because derivation is not super important for KCET students. For board, yes it is important, and I have already covered in a separate video, so you can go and check that out. So here we have a current carrying wire which is carrying some current, say I. Okay, the radius of the loop is r. Now it is a 3-dimensional loop and I am trying to show it in a 2-dimensional, so it might appear that the loop is not circular, but it is circular. But if you are watching from certain angle, then you will see only like this, right? So here is the point where you are trying to find the magnetic fields at a distance x from the center of the loop. So what will be the magnetic field at this point? So the magnetic field at this point, general expression is given by mu naught I r square divided by 2 into x square plus r square to the power 3 by 2. Very important formula to remember. Okay, very important formula to remember. and if you are trying to find the magnetic field exactly at the center of this loop, then you have to put x equals to 0 in this above expression, and it becomes mu naught I by 2r. These two formulas are very, very important for KCET. Okay, we can go a little bit further. That is, if you are trying to find the magnetic field at a very far away point, such that the radius is very small compared to this distance. Okay, the radius becomes smaller. The value, suppose the radius is 2 centimeter. The distance initially was 5 centimeter. So 2 centimeter, 5 centimeter are comparable, you cannot ignore. But suppose the distance is now 5 meter. 5 meter and 2 centimeter, you can easily ignore 2 centimeter, that is only 0.2 meter, whereas 0.02 meter, whereas 5 centimeter is almost 5 centimeter. So 5.02 and 5 are almost same. So you can ignore the radius, and you can put r equals to 0 in this expression for the denominator part, where it is getting added with this x square. Okay, the numerator r will still be there, even if it is small, you cannot ignore the numerator r square. So only denominator you can put this r square to 0, so you will get 2x cube. So x square to the power 3 by 2, so 2 cancels and you get x cube over here. Okay, now what we will do, we will reorganize it little bit. How to do that? We will multiply pi in the top and bottom. So once we multiply with pi, then we get in the top, we get pi r square. Now what is pi r square? For a circle, pi r square means the circular area, right? Area of the circle is given by pi r square. So pi r square is giving you the area of the circle. So we will replace pi r square with the term with the term a, and we get mu naught by 2 pi x cube I into a. Now I into a is called dipole moment due to a circular current carrying loop. I into a is defined as the dipole moment due to a circular current carrying loop, small m. So if you put that value, you will get this as m by 2 pi x cube, and if you reorganize a little bit, you will get mu naught by 4 pi 2m by x cube. So B is mu naught by 4 pi 2m by x cube. Now if you remember, there was a similar expression, that is electric field due to the dipole on the axial plane. Electric field due to a dipole on its axis was given by a similar formula, right? So it was, axis was given by 1 by 4 pi epsilon naught 2p by r cube, right? That was the axial case. Similar to that, here you are getting a magnetic field. It was electric field, it was magnetic field on the axis of the circular current carrying loop. In fact, a circular current carrying loop can behave as a magnet. Okay, a circular current carrying loop will behave as a magnet of dipole moment is given by I into A. I into A is the dipole moment of the magnet, and you can find its dimension, its unit as well. So dimension of current is ampere and dimension of area is meter square. So ampere meter square is the dimension of dipole moment. Okay, so this is magnetic dipole moment. Dipole moment, and it is denoted by the symbol small m, right? Now let us compare, because we now have compared between electric field due to a dipole and magnetic field due to a dipole. Let us do a general comparison between magnetic field and electric field. Both are long range. Okay, both are long range, since both depend inversely on the square of the distance from the source to the point of interest, right? So it can vary from the as you know, the magnetic field becomes 0 at infinity, electric field also becomes as 0 at infinity. So they are long range, right? Earth's magnetic field is way beyond the boundaries of the surface of the earth, and it is protecting us from all the cosmic harmful rays that is coming towards us, and it is protecting us, right? It's acting as a protecting shield because it's very long. That's why it can protect us. If it was very short range, we may not be able to survive on earth. Okay. Next is the principle of superposition applies to both fields, right? So magnetic field and electric field both have, if two fields combine, then you will get a resultant field which is a vector sum of the individual fields. So both have the both obeys the superposition principle. The electrostatic field is produced by a scalar source, namely the electric charge. So in case of electric field, we had a source, that is a charge. If you have a charge, there will be a electric field around this charge, right? And that is a scalar source. Why? Because charge is a scalar quantity. So electric field is produced by a scalar source, whereas magnetic field is produced by a vector source. What is that? IDL. So I already told you IDL cross R cap, right? That was the Biot-Savart's law, similar to that of Coulomb's law. So IDL is a vector source, okay? It has a direction. So if you are considering a current carrying wire, then this will be the direction of IDL, okay? DL will be in the direction of current, right? So IDL is a vector source, whereas in case of electric field, it was a static source, or it is a static charge, right? The electrostatic field is along the displacement vector joining the source and the field point. The magnetic field is perpendicular to the plane joining the displacement vector and the current element IDL. So if you are considering the direction of electric field, direction of electric field is how? Either it will be towards or it will be inwards based on the charge. If it is positive charge, it will be away. If it is negative charge, it will be towards, right? So electric field is joining the line from the point and the charge, right? Electric field is always along the line joining. It can be in towards or outside based on the nature of the charge. If the charge is positive, it will be always out. Now in case of magnetic field, it is IDL cross R vector. So IDL in this direction, R vector in this direction, right? So what will be the direction? So it will be IDL cross R. So IDL cross R means it will be perpendicular, mutually perpendicular to both of the vectors, right? So cross product means IDL cross R, so it will be the direction of the vector. So both perpendicular to both. So that is the nature of cross product, right? Cross product gives you a vector which is perpendicular to both the original vectors. There is an angle dependence in the Biot-Savart's law which is not present in the electrostatic case. So if you take the scalar form, Coulomb's law in vector form, Coulomb's law in scalar form, Biot-Savart's law in vector form, Biot-Savart's law in scalar form. So in the scalar form of Biot-Savart's law, there is a sin theta which is present, right? Ideal sin theta. But in case of Coulomb's law, there is no such sin theta. So from there we can say that the magnetic field at any point in the direction of DL, the dashed line is 0. Along this line, Q is 0, sin Q is 0, and dB is 0. Okay. So if you can find a direction, particular direction, for example, if you consider the magnetic field in this direction, okay, suppose what is the magnetic field? It is your point, your DL is over here, and you are trying to find at this point P what will be the magnetic field. Okay, so in this case, if you consider DL and R both are in the same direction, both in the same direction means DL cross R will be 0. Right, DL cross R will be 0 because sin theta is 0, sin 0 is 0, that means magnetic field will also be 0. Okay, so it will not Q, it is theta. Okay, theta is 0, that means sin theta is also 0. Now let us do a small derivation of the relationship between mu naught and epsilon naught. Okay, so mu naught into epsilon naught. Let us try to find the multiplication of these two vectors, these two quantities. Okay, so mu naught into epsilon naught we are trying to find. So this is what we are starting with. This is our starting point. Okay, now what we are doing, we are multiplying 4 pi epsilon naught, 4 pi here and 4 pi over here. So basically what we are doing, we are just multiplying with 4 pi and dividing by 4 pi. Okay, so if you do that, then you will get what is the value of 4 pi epsilon naught? 4 pi epsilon naught is given by 1 by 9 into 10 to the power of 9. Why so? Because 1 by 4 pi epsilon naught is equals to 9 into 10 to the power of 9. So 1 by means if you take inverse in both sides, then you will get 1 by 9 upon 10 to the power of 9. Now what is this value? Mu naught by 4 pi. Mu naught by 4 pi is 10 to the power of minus 7. Right? Now let's take this value in the division, and it will become 9 plus 7. So it will be 10 to the power of 16. Okay, 9 into 10 to the power of 16. Now 9 into 10 to the power of 16 can be written as 3 into 10 to the power of 8. Now what is 3 into 10 to the power of 8? 3 into 10 to the power 8 is nothing but speed of light in vacuum, right? So speed of light in vacuum is given by 3 into 10 to the power of 8, right? Now you can take the inverse on both sides. So in this side 3 into 10 to the power of 8 will be in the numerator, whereas here it will be 1 by epsilon naught mu naught. So that value is equals to c, so we can write this as c square, right? 3 into 10 to the power of 8 whole square, so that can be written as c square, and from there we can show that c is exactly equals to 1 upon mu naught into epsilon naught. Okay, so this is a important relation to remember. Okay, the derivation I have not seen coming in recent times, but you have to remember the values. That's why I have done this derivation for this simple derivation. Now here c is speed of light. Okay, epsilon naught is permeability of free space, epsilon naught is permittivity of free space. So this is the relationship between c and mu and epsilon. Okay, if the this is for speed of light in vacuum, that's why both are 0 0. Now speed of light in any other medium, speed of light in any other medium is given by 1 by square root of mu into epsilon. Okay, mu into epsilon means the permeability of that particular medium, and epsilon is the permittivity of that same medium, right? So that's why you can see that if you put the values of mu naught and epsilon naught in terms of relative permeability and relative permittivity, then you will see that the value actually less than that of c. Okay, that's why speed of light in vacuum is always the highest. In any other medium, speed is always less than that of c. Okay, now let's solve one question. In the given figure, the magnetic field at O, is given by. So here, if you start with this diagram, you have to remember that this is a part of a circle, right? If you complete this, if you ignore this part for now, then this would be a circle, right? This will be a simple circle. Now what is the magnetic field due to a circular current carrying wire? Magnetic field due to a circular current carrying wire at the center is given by mu naught I by 2r, right? Mu naught I by 2r, that is the formula for magnetic field at the center of a current carrying loop, right? This is the magnetic field at the center of a current carrying loop. We did this calculation few moments back, right? Now this is due to a complete circle, but this is not a complete circle. So you can divide this circle into 4 equal parts: part 1, part 2, part 3, part 4, right? This is due to entire circle, right? And it has 4 equal parts: 1, 2, 3, 4. So what will be the magnetic field due to any one of this part? So magnetic field due to any one of this part will be equals to 1 upon 4, right? 4 parts, due to 4 parts it's complete, but if you consider any one of the value, that will be 1 by 4 of that entire value, right? Now how many parts are present in this given case? If you see, 1, 2 and 3 are present, whereas 4 is missing. 4 missing means only 3 parts will contribute in this formula. 3 parts will contribute in this formula. That means it will be 3 by 4. Okay, so this is the magnetic field due to this part of the circle. This will be the magnetic field due to part of this circle. So let me rewrite this. You can write this as 3 by 8 mu naught I by R. Okay, this is the magnetic field due to the part of this circle. So if you see that there are two options having the same values, right? 3 by 8 mu naught by R, 3 by 8 mu naught by R. So what will be the magnetic field due to the other part, that also you have to calculate, right? Now what is the direction of this magnetic field? The direction of this magnetic field, to find that you have to use your fingers, curl it in the direction of the current. Current is flowing in this direction, right, in this direction and going out. So magnetic field will be, if you take the finger and curl it in the direction of current, then your thumb will give you the direction of the magnetic field. So magnetic field in this case is into the paper. Into the paper means, how do we represent into the paper? To represent into the paper, we have to use a cross sign. Cross sign means it's like a target, dartboard. If you play dartboard, so you are throwing towards the target, right? So this is the target, that's why it is going into the paper. That is the representation of means. Now there are two other wires. One wire is carrying current in this direction, another wire is carrying current in this direction. Now in this particular case, the wire is carrying current which is passing through the center, not directly, but if you take a angle, you will get to see that this is actually carrying the current in the direction of the from the center, right? So from the center means magnetic field due to a straight current carrying wire. Magnetic field due to a straight current carrying wire is what was the expression? It was mu naught I by 2 pi r, but that is in the perpendicular direction. And if you remember, if the point passed through this same line, the magnetic field becomes 0. That was also we have shown, right? Same line means ideal and r vector in the same direction, cross product becomes 0. That means the magnetic field basically becomes 0. So due to this, we will not have any magnetic field. Due to this wire, we will not have any magnetic field because it is passing through the center, directly through the center. This wire, however, is not passing directly through the center. It is at a distance r. Okay, it is at a distance r, right? So what will be the magnetic field due to this wire? Magnetic field due to a infinite wire, magnetic field due to an infinite current carrying wire is given by mu naught I by 2 pi r at a distance r, right? Now is this an infinite wire? It's starting somewhere at infinity. It is starting somewhere at infinity and it is coming, but after reaching over here it is bending, right? So you cannot consider this to be an infinite wire, but this part is infinite, right? This half is infinite, this half is not infinite. So what we can do, we can consider that this wire, imaginary wire, if it is very very long, infinity has both sides. Now if you cut it from here, what will be the magnetic field due to this half of the wire? Magnetic field due to this half of the wire will be nothing but half of this. For a complete infinite wire, it will be mu naught I by 2 pi r, but half of the wire, it will be half of that exact value. So it will be mu naught I by 4 pi r, not 2 pi, sorry, 4 pi r, right? So mu naught I by 4 pi r. Now what is the direction of this wire now? For circular current carrying wire, you take your fingers in the direction of current. For circular current carrying wire, you take your fingers in the direction of current and thumb represents the magnetic field. For a straight current carrying wire, it is exactly the opposite. You first point your fingers in the direction, you point your thumb in the direction of current, okay, then curl your fingers, that direction is the magnetic field. So in this case also, the magnetic field, the current is in this direction and magnetic field will be into the page of the paper again. So it will be into the page of the paper again. So this magnetic field is also cross. So both magnetic fields are cross. That means the resultant magnetic field, the total magnetic field is basically 3/8 mu naught I by R plus this value mu naught I, that is mu naught I by 4 pi R. Okay, small r, capital R is same, okay, because only small r is given, so let me write small r over here as well, right. So you can see that only one of the answer is correct, which is this one, option A. So if you see, both options are same except the negative and positive sign. Okay, so there will be some confusing question like this. If you are smart and if you have complete thorough understanding of the theory, then definitely you can answer such difficult question, and it is from KCET 2020. Okay, it is not very far as well, not very older as well. Okay, and so this is the basic concept that you have to understand, that first you remember the value of the magnitude, then based on the given shape and the design you have to divide it and then calculate it exact value, and then whether they are in the same direction or in the opposite direction, you have to add them or subtract them. Clear? So with this note, I would like to close this video, but I have two homeworks for you as usual. So let's solve these homework questions. Homework question are slightly easier. First homework question at least slightly easier. So try to solve this question and mention the answer in the comment section of this video. And for the lecture notes, you have to go to our WhatsApp channel. The link of the WhatsApp channel is given in the description. Again, this question is slightly tricky but not super difficult. Try to pause this video, read this question carefully, answer it, and then mention the comment answer in the comment section of the video, main comment section, not in the live comment. Mention in the main comment section of this video. I'll be back with part 2 of this video. Till then, bye.